Hello. Remember that a complex system consists of these little entities, these agents, these parts that have interdependent payoffs and rules that create emergent phenomena and robustness and possibly large events. In this lecture, we're going to talk about a fundamental trade-off for the agents within a complex system. And that trade-off involves whether to explore or whether to exploit. So first, some basic definitions. By exploration, I mean searching for better solutions, climbing on that landscape. The more you search, the more likely you'll locate a really good choice of action. By exploitation, I mean taking advantage of what you know, reaping the benefits of past searches. This trade-off between continuing to search to explore or to rely on what you've already learned to exploit is common for actors within a complex system. Suppose, for example, you want to find a deli in New York. New York has thousands of delis. In addition, new delis are popping up all the time, and existing delis adapt. They change their menus and suppliers. If you desired, you could explore forever. But if you did this, if you kept exploring, on average, the quality of that corned beef on rye that you're eating would be just average. So at some point, what you've got to do is you've got to exploit the information that you've gathered. But if you stop exploring, if you go the other way, if you just exploit what you know, you could miss out on something much better. Or even worse, your loyalty and that of others could cause the quality of your favorite deli to decline, and what was once a really great place to eat may now be just sort of mediocre. So ideally, you shouldn't either stand pat or continue to explore. What you need to do is balance exploration against exploitation. In this lecture, what we're going to see is how and why actors in complex systems maintain this balance. And in addition, we're going to see how doing so actually maintains complexity. But we're only going to get to that at the end. All right, recall from a previous lecture that a system with very few connections and interdependencies won't produce complexity. Instead, it's just going to be a bunch of isolated independent events. But if we had too many connections and interdependencies, the result would be some sort of incomprehensible mangle or gray goo, right? So the domain of complexity exists in this interesting in-between region where we've got some connections and some interdependencies, but not too much. That same logic held for diversity and adaptation. Complexity happens in the region in between. But this begs the question, if complexity happens when those dials, remember our 4 dials, are adjusted just right in the center, how do they get there? Well, in this lecture, we're going to give a possible answer as to why. We're going to begin, though, by describing this explore-exploit trade-off, because that's going to be the basis for this fundamental insight. And we're going to do it in the context of a rugged landscape problem, a decision problem called the two-arm bandit. This problem requires choosing between 2 arms on a slot machine. After we do that, we're going to return to 2 concepts from the second lecture, rugged landscapes and dancing landscapes. And we're going to see how the explore-exploit trade-off manifests itself in those 2 contexts. And along the way, we're going to introduce a really cool algorithm. That's just a search procedure that balances exploration with exploitation, and it's called simulated annealing. This algorithm abstracts from a process used in physics and engineering, the annealing of glass and metals, and constructs an algorithm, a heuristic, that can be used to solve problems. We're then going to turn to evolutionary systems and see how the basic mechanisms of evolution, mutation, recombination, and selection, can be seen through this prism of exploration versus exploitation. Species in an ecology, just like firms in a market, confront this tension between explore and exploit. And then finally, we're going to use this idea, this explore-exploit trade-off, to propose a possible explanation for why systems tend to be complex. Okay, let's go to the two-arm bandit problem. If you walk into a Las Vegas or Atlantic City casino, you're going to see hundreds, if not thousands, of people sitting there dutifully pulling the levers of slot machines. In some places, these levers have been replaced by buttons, but for imagery, I want you to think that people are pulling levers. Most slot machines have a single lever, and these machines are designed so that on average you lose money. I hope that doesn't shock anyone, but they are, and hence they're called one-arm bandits. You put in money, you pull the lever, you win some, you lose some. As the old saying goes, you pays your money, you takes your chances. But think of a slot machine not with 1 arm, but with 2 arms. Now the key assumption here is going to be that these 2 arms pay out at different rates. To keep this experiment simple, I want to imagine that it costs $1 to pull the arm, and the machine pays out either $10 or it pays nothing. Now the only difference between these 2 arms is going to be the frequency with which they pay the $10. Now I'm going to give you $1,000 in seed money, and you've got 1,000 pulls, right, to make as much money as you can. How are you going to do this? How do you allocate your pulls across the levers? Or more appropriately, what should you do if you were optimizing? What you should do would be to take maybe the first 10 or 20 pulls and explore. So you might take 10 pulls of the right lever and 10 pulls of the left lever and compare the payoffs. So if the right lever paid off 3 times and the left lever paid off twice, you might think, well, maybe I should pull the right lever more. But this would be exploiting the right lever. Do you exploit the information you've gathered so far, or do you continue to explore? 10 pulls isn't very many, and 2 wins is pretty close to 3. And so what you may do is decide to, give 10 more tugs on each arm. Suppose after these 10 more tugs, you have a total of 6 wins on the right arm and only 4 on the left arm. Well, now it might seem like a really good time to start exploiting. And you might be smart to allocate your next 10 pulls to the right arm. And if again you found that 3 or more of those pulls pay off, you might be justified to stick with the right arm for your last 900 and some pulls. But if you only get 1 or 2 payoffs in the next sequence of 10, you might decide, well, I think I'm going to go back and explore a little bit more with that left arm. All right, now you've got the basic idea. The more you explore, the more likely you are to find the correct lever. That's a good thing. But the more you explore, the less time you spend taking advantage of your information. That's a bad thing. The optimal solution to the two-arm bandit problem depends on the number of pulls you get and on the information you receive along the way. So for example, if the right arm always paid off, you should keep pulling it forever. You might never even pull the left arm. Alternatively, if the right arm pays off only 1 in 20 pulls, and the left arm pays off only 1 in every 25 pulls, you might spend most of your 1,000 pulls exploring and little time exploiting, because the difference is so small and the payoffs are so rare. Okay, now we've got this basic idea down, this tension between exploration and exploitation. I want to take that basic idea and I want to go back to our concept of a rugged landscape and a Mount Fuji landscape and describe how that trade-off plays out there. Okay? Now recall from the second lecture that we can think of the possible actions that an entity might take. This could be a frog, a person, or the FDIC as a set of geographic coordinates. And we can think of the fitness of what that behavior is, or this would be the fitness of a species, or the happiness of an individual, or the success of a policy in terms of elevation. And this gives us a landscape. Remember, right? The landscape can be either something like Mount Fuji, it can be very simple, or it can be rugged like the Appalachians or the Rockies. So let's go back to the idea we had of a hiker climbing on a landscape, searching for some point of high elevation. The ambition of this hiker is to get as high up as possible. Okay, if time wasn't an issue, the hiker could check every point, explore forever, and then just choose the best point. That's easy. But the hiker, like us, has only so many grains of sand in his hourglass, so they're insufficient to perform this sort of exhaustive search. As the great philosopher Groucho Marx once said, "Time flies like an arrow, fruit flies like a banana." So given this limited time, given that time does fly, we can't search forever. We have to balance off exploration with exploitation. We have to learn what we can do, and then take advantage of what we've learned. The same is going to go for our hiker. He doesn't want to spend too much time searching around. He wants to get to high ground as quickly as possible. Okay, so here we've got our hiker, and let's suppose he takes his first step. He starts to explore. He's going to stay at this new step, this new point, if this location is higher than where he was before. So if his step leaves him upwards, he's going to stay there. If it takes him lower, then he'll return to where he was, because, he's worse off. Starting from any point, the hiker has 4 directions to test, to the north, south, east, and west. If any one of these 4 directions leads him uphill, he'll take it. If none do, though, he's going to stop. Recall from the Rugged Landscape lecture that this is a local, if he's at some point where north, south, east, and west are all worse, this is what we call a local peak, a local optimum. If our hiker uses this rule of only going up, and what he's going to do is he's going to climb until he finds a local optimum, and once he finds one, he's going to stop. Well, is this a good thing or a bad thing? Well, let's put him on Mount Fuji. If we put him on Mount Fuji and set him loose, he's going to clamber right up the side of the mountain to the peak. Excellent. He's at the global optimum, he's at the global peak, everything's fine. Okay, let's put him in the Appalachians or the Rockies on a rugged landscape. In this case, this search rule is going to perform really poorly. He's going to climb the first hill he gets to, he's going to stand atop that peak, and he's going to be stuck. On average, this isn't going to be a very good solution. So as this example suggests, just climbing uphill is not a very good approach to finding a solution unless the problem is really simple, unless it's a Mount Fuji. Computer scientists refer to this sort of search as a greedy algorithm. Now, as the name suggests, being greedy isn't necessarily a good thing. So what we need is we need a more nuanced search approach that's going to enable our hiker to get off these local peaks. This search approach has to do a little bit more exploring and a little bit less exploiting than the greedy algorithm. The search approach I'm going to describe is called simulated annealing. Simulated annealing is a search algorithm that was designed by computer scientists actually working at Los Alamos National Labs as part of the Manhattan Project. We're going to study this search algorithm for 3 reasons. First reason, it works. So that's a good thing. That's always a good reason to study it. Second, it's going to provide a segue into the concept of self-organization, which we're going to study in a later lecture. Third, it's going to show this sort of fan-out nature of complex systems, the idea that we're really focusing on concepts and ideas that apply widely. They fan out into a lot of disciplines. So what we're doing here is we're taking a really cool idea, an algorithm we're taking a cool idea from physics and engineering, and we're turning it into an algorithm from computer science, and we're going to apply it to people trying to find a good deli. So this is just great. It's totally fanning out. A good place to start when we talk about simulated annealing is to talk about annealing. What is annealing? Annealing is a process that's used to harden glass and metals or to make crystals. So let's suppose I've got a piece of glass or a bit of sort of preformed metal, and you can think of these as a whole bunch of little particles. That's really what they are. So this isn't very hard to imagine. And what I want to do is I want to think about how they're formed. So what I want to do is I want to introduce a stylized model of a glass or metal or a crystal, and this is known as a spin glass. So what a spin glass is an enormous checkerboard. And on each cell, each square in the checkerboard, is a little particle. And each particle has a spin, which either is +1, which is pointing up, or -1, which is pointing down. Now initially, I'm going to just randomly assign these spins. So I'm going to freeze the system in that state. So some of the spins are up, some of the spins are down. The system is what we call disorganized. Okay? Got the picture? There's a huge checkerboard. Each square has a little particle on it that either points up or points down. What we'd like to do is get all of these particles to point in the same direction. Then we'd have the spin glass would be organized. Now, if the spin glass is organized, what this would be is tempered steel, hardened glass, or a crystal. There would be the structure with everything pointing in the same way. Now, we don't care whether they're pointing up or whether they're pointing down. What we care about is they all point in the same direction. How do we do it? Well, we anneal. So one thing we could do is we could go in and turn each particle. That won't work. It would take a ton of time, and we'd need really, really small tweezers. What annealing does, and this is what glass makers and metallurgists do, is they take advantage of the fact that the particles actually want to line up. So if we think of these particles as like little agents, they want to point in the same direction. So when the metal's too cold, when it's frozen, these particles are all stuck in this frustrated or this disorganized state. So the physicists call this frustrated, and you can literally think of these little spins like people you know. If they're not organized, right, they're frustrated. Now, if we heat the metal, these particles become unfrozen. They're set free to do whatever they want to do, and they're going to try and align their spins with those of their neighbors. So the trick would seem to be here to heat the metal so the particles are free to move around and line up with their neighbors. So if we did this, if we put the heat up really high, they'd all start sort of spinning around, and they wouldn't settle down. So that's not going to work. So what we need to do is we need to heat the metal just enough so the particles get free enough to move, but not so much that they can dance around like, just spinning in all sorts of crazy directions. So if we heat it up just enough, each particle is going to try to match the direction of its neighbors. And what's going to happen is locally in little regions, all the particles will align. So they'll either all point up or they'll all point down. Now, the problem is going to be this. Now we're going to have local neighborhoods that possibly differ. So we may have one region where they're all pointing up and an adjacent region where they're all pointing down. And the result will be sort of like a camouflage pattern where some regions point up, some regions point down, and this boundary is disorganized or frustrated. Now, once this camouflage pattern starts to form, what do? We think, well, we're doing pretty well here. Let's cool the temperature a bit. This is annealing. When you cool the temperature, what you do is you sort of lock in the region that's up and lock in the region that's down, right? But the particles on the boundary that are frustrated, they're going to keep flipping a little bit because they don't know which way to go. So there's still some heat in the system, so the boundary can keep flipping, even though the centers stay fairly fixed. What this means, though, is that the boundary can move. As parts of the boundary become, start pointing up, then parts that were in the pointing down region are now on the boundary. So the boundary is going to move around and sort of get absorbed into one region or another. So here's how this is going to happen. Imagine you've got a small neighborhood of particles pointing up. Say just like 16. There's 16 little holdouts surrounded by a bunch of particles pointing down. At some point, the boundary of that region of the 16 particles is just going to start to flip, and that little region is going to shrink from 16 to 12 to 8 to 4, and eventually that whole region, instead of pointing up, will point down. So because these boundaries move eventually, the whole checkerboard is going to come into the same state. And once we've got all the particles pointing in pretty much the same direction, with the caveat there may be still a few little bits of flipping around on some boundaries, we're going to lower the temperature a little bit more. So this is more annealing. As the temperature cools, eventually all the particles are going to stabilize in such a way that they're pointing in the same direction. In our case, that direction is down. And when they all are pointing down, we cool the temperature so far that the system freezes, that it becomes organized. And we call this state organized, again, right, because all the particles are pointing in the exact same direction. Okay. Annealing then works as follows. You heat up the glass or metal, free the particles from their surly bonds. Then you slowly lower the temperature so they can align locally. This creates neighborhoods or regions that point mostly in the same direction. You keep things hot enough so that the neighborhood boundaries keep moving. This allows the neighborhoods to align as the boundaries sort of move about. Once the neighborhoods are aligned, your particles are all organized, and what you do is you cool the whole thing off. Okay, that's annealing. We've now got an idea how annealing works. We want to take that idea and apply it to our hiker on the rugged landscape. In a nutshell, we want to heat things up and then slowly cool things down. It's a lot like how we approach the two-armed bandit problem. First we explore, that's having heat by having lots and lots of heat, and then we exploit by cooling things down. How fast we cool depends on properties of the particles and the metals and glasses. So metals and glasses are annealed at different temperature schedules. Okay, now let's go back to our landscape and let's think about a simulated annealing algorithm, because we're not actually going to heat up our hiker. We say simulated because what we're going to do is we're going to use the idea of heating and cooling to find a point of high elevation on the landscapes. Here's how this is going to work. We want to think of the temperature as a proxy for the probability of making a mistake. When the temperature is high, that means the hiker is going to make a lot of mistakes. When it's low, he makes almost no mistakes. What is a mistake? A mistake for a hiker is going downhill instead of uphill. Okay, let's start out. Let's make the temperature really, really high. If the temperature is really, really high, it's as though our hiker doesn't know down from up. He's going to make a ton of mistakes. He's just like one of those little particles who's just sort of flipping up and down. He's going to be dancing all over the place. What he's doing is he's doing lots of exploring. So he's going to just take a step and he's not really going to know whether it's up or down, so maybe he stays there, maybe he doesn't. But because the temperature isn't too high, he's probably a little bit more likely to go uphill than downhill. Now what we want to do is we want to cool the temperature a little bit more. And as we cool the temperature, he becomes a little bit more discerning. So he still goes downhill occasionally, but just not as often. And eventually what we're going to do is we're going to cool the temperature all the way to 0, and he becomes sort of his old greedy self. He uses that greedy search algorithm where he only goes uphill and he never goes downhill. Okay, now we have to ask, okay, so we get what simulated annealing is. We start out with lots of mistakes, we cool the temperature, we make fewer mistakes, and eventually there's no mistakes. Does it work? Okay, well, let's look at our two types of landscapes. Let's start with Mount Fuji. On Mount Fuji, instead of just climbing up the hill like he did before, a hiker sort of roams around a bit. He mostly goes up, but he sometimes goes down. As we cool the temperature, then he starts going down more and more rarely, and he's mostly going up. So on balance, what it means, he's going to be moving up the slope. He's just not going to be running up the slope like he did before. As the temperature gets even cooler, then he starts almost always going up. He takes many, many steps up for each step back. And he's pretty much going to be near the peak after a while. Eventually, though, when we drive that temperature down to 0, when we don't allow him to make any mistakes at all anymore, he's going to get right to the peak, and he's going to stay there forever. So the result of this annealing is he's going to get to the peak. He's just not going to be as quick as his greedy self was. But the important part is that he does find the peak. Okay, now, let's put our hiker in the Appalachians. So again, we're going to start with a high temperature. He's going to explore a lot, and then we cool it a little bit. So maybe initially 55% of the time he goes up, 45% of the time he goes down. Let's suppose he's at the top of a huge peak. It'll take many steps down in a row to get off that peak, so it's not likely he's going to do it. Even the slightest drift upward will be enough to keep him not at the peak, but at least on this sort of, near the top of this big mountain. But let's suppose he's on a tiny little hill that's only 2 steps up, a little hillock. Okay, now it's very likely, because he allows himself to make mistakes, that these mistakes will let him walk off that little hillock. Why is that? Even though he tends to go up, it's the fact that he allows himself to make several mistakes in a row because of the high temperature, that he can get out of that little hill. Now, over time, the errors are going to allow him to escape almost any little hill, but not to escape big mountains. Now, as the temperature starts to cool even more, the hiker is going to remain at or near the local peak he's on. And when the temperature cools all the way, he's going to become greedy and he's going to rush exactly to that local peak and he'll stop. So what's going to happen is annealing is going to give him a pretty good solution. Not necessarily the optimal peak, the global peak, but it's going to put our hiker on a fairly big hill, because annealing enables the hiker to do a lot more exploring than he previously did. It allows him to sort of get off on one of those, any little hillock. And at the same time, the gradual cooling enables him to exploit what he's learned. So if we think over these 2 landscapes, Mount Fuji and the Appalachians, we see that by having this cooling temperature, you can sort of get off little hills and get to bigger hills. And you realize if you had an optimal cooling schedule, if you could figure out exactly how to anneal, you'd want to change that schedule as a function of the landscape. So on Mount Fuji, you'd want to cool that thing off as fast as possible. On more rugged landscapes, you'd want the cooling to be slower. I want to take a brief sidebar here and talk about how evolution does this, how it balances exploration and exploitation. So let's restrict attention to species that have sexual reproduction. So what do we have? We've got mutation and recombination of genes. So when we have sexual reproduction, we have the crossing of genes, and we have this recombination, and we also have these errors introduced by mutation. These are forms of exploration. This isn't like annealing when the temperature's hot. By mixing the genes of 2 parents, the offspring can be thought of as new searches. So what we get is we get that recombination and mutation are example of exploration. Well, what's exploitation? Exploitation is just selection. Individuals that are more fit are more likely to produce. They're better solution. So a better solution to the problem of how to make a cockroach, right? A better cockroach is more likely to be in the population that gets mutated and recombined. Let me play this out a little bit more for a second. Remember back to our indigo buntings from the previous lecture. If there's a lot of variation in the population of indigo buntings, what that means is it's almost like the temperature being high. It means when those species reproduce, when those indigo buntings reproduce, there's lots of things that they can get. It's a high temperature. When the variation is low, what that means is that there's not much diversity that's going to be produced. There's not much exploration that's going to go on. That's like having a low temperature. So what evolution does is that by changing the variation in the species, it can adjust the temperature. All right, this model, the idea that genes produce fitness, is sort of a gross simplification of how evolution works. We've talked about this before, but developmental pathways from DNA to fitness depend on all sorts of factors, including RNA, epigenesis, and who knows what. Our understanding of the mapping from genotype to phenotype deepens daily. That said, what we're doing here is we're painting in some very broad strokes, and the crude picture has some value. And what that picture shows us is that evolution is confronted with this same problem of how do we balance exploration and exploitation, and how do we do this through selection, recombination, and mutation, and population variation. Okay, we've now got this basic understanding between exploration and exploitation, and we want to apply it now to dancing landscapes, to complex systems. So I want to look at a particular complex systems first in some detail, and then from there we'll draw some conclusions. What I want to look at are leafcutter ants. Okay, some background. Leafcutter ants reside in tropical or semi-tropical regions. These are farmers, literally. They raise crops. They don't raise peas or beans or corn. What they raise are fungus. Now, how do they do this? They go up and they climb trees and they cut leaves from the trees with their little mandibles. This isn't done in some sort of pell-mell fashion. Leafcutter ants come in a whole variety of sizes, and each one of these different sizes plays a different role. So once they've cut these leaves and carried them back to the nest, they've got ants that chew them. So the bigger ants first chew the leaves into smaller pieces. Then the smaller ants chew these remnants into even tinier fragments. Finally, there's these itty-bitty little ants that chew these fragments into a pulp that gets consumed by a fungus known as Gonglydia. Now, these aren't cute little colonies. They're massive productive systems. They're like giant factories. A leafcutter colony can have, 8 to 10 million residents. There are instances of leaf-cutting colonies forming what are called foraging lines. They're like superhighways, 250 yards long, right, from a tree all the way down to this nest. We'll talk about how these paths get created when we talk about emergence in a later lecture, okay? But for the moment, what I want to think about is we've got these farmer ants. And you might say, okay, what does this have to do with dancing landscapes and exploration versus exploitation? Okay, wait. First, the trees are trying to avoid getting eaten by these ants, or at least they want to limit the damage. So you've got this standard sort of co-evolutionary story going on there between the trees and the ants. But it's more complicated than that. Because you've got these ants then that take these leaves and they create a fungus. Well, the fungi the ants are producing attract bacteria. So when they build this giant fungi factory, this giant mushroom factory in the forest, what the leafcutter ants are doing is they're creating a giant food source for bacteria. They're basically putting up a giant sign, all bacteria eat here, right, as well as for themselves, right? So this diner serves both themselves and the bacteria. Well, here's the problem. Bacteria can reproduce a lot more quickly than ants. So how are the ants possibly going to fight the bacteria if the bacteria are able to explore much more quickly than the ants do? What the ants do to combat this bacteria is they've actually evolved an antibiotic line of defense. Now, how do they do this? Well, the ants, it turns out, have their own bacteria. They have a bacteria that grows on their backs, literally. And this bacteria that grows on their backs can attack the bacteria that eats the fungus. So what we see here in this very brief description of an ecosystem is this constant balance between exploration and exploitation. We've got the ants trying to exploit the trees and trying to exploit their knowledge to build this sort of fungus factory. And at the same time, they've constantly got to be exploring, using the bacteria on their backs, new ways of fighting the bacteria that's eating their fungi. So there's constantly reasons to explore. So what happened is that leafcutter ants had to form a relationship with the bacteria in order to evolve fast enough, in order to keep exploring. And metaphorically, again, we can think of this as maintaining their elevation on this dancing landscape. Okay, this logic holds writ large. What was once a very good solution could be a lousy solution once a landscape is shifted. Anyone or anything placed on a dancing landscape, whether it's a bluegill, whether it's Microsoft, or your Aunt Tessie, had better maintain some amount of exploration. Just like sharks have to keep moving or risk death. The same is especially true for firms. They must, as the title of a famous management book says, innovate or die. Okay, now we're at the sort of, I think, the key point in this lecture. We see that the landscape is dancing. It's incredibly important to keep exploring. Now, we saw on a rugged landscape, there's this balance between exploration and exploitation, but we could sort of anneal over time and eventually do more and more exploitation. How early on it made a lot of sense to explore, but later on we want to exploit. And this was the sort of the undergirding for the algorithm simulated annealing. We start out exploring and we end up exploiting. But on dancing landscapes, and this is the key point, the agents can never stop exploring. They can't. If they did, what they'd find is that what was once a peak might now be a valley. And this, more than anything else, may explain why we see so much complexity. So think back to our leafcutter ants and the bacteria in the trees. We've got this collection of coupled landscapes. Or let's think of a collection of competing firms. Suppose every firm is sitting at a local peak. So suppose we don't have complexity. We're in some sort of nice equilibrium. And we've got these dancing landscapes that become fixed. Well, once this happens, once nobody else is moving and the landscape stop dancing, now there's incredible opportunity to explore for new and better peaks, right? Because you've got a fixed problem. We talked about this in the context of the Manhattan Project. Well, once you've got all this time to look for a better peak, if you find it, if you find some better solution, you're going to take that action. But when you take that action, what you do is you make the landscapes of the other firms dance. So those other firms are then going to start moving around on their landscapes. So agents that explore, whether they're firms or the bacteria on the backs of the leafcutter ants, are preventing stasis. They're keeping the system from churning. So now we understand why adaptation keeps the landscapes dancing. But that begs the question, why don't we get utter randomness? Why don't we just have the whole thing constantly in flux? Okay, that's a great question. Well, if all the firms were constantly changing their strategies and prices, or if all the species in an ecosystem were constantly moving, then a really good strategy would just be to stick to something basic. It'd just be too crazy out there. It'd just be this mangle. Well, if in the presence of total randomness, it becomes impossible to explore and you just stick to some simple thing and exploit, right? What you're going to do is you're going to cause the system to stabilize because the benefits from exploration have fallen so much that the relevant benefits of exploitation increase, and it makes a lot of sense to just stand pat. So this is why systems don't get too crazy. And it's the reason why we see so much complexity about us, is exploration prevents stasis, But the necessity of predictability in order to explore puts a limit on how crazy things can actually be. Okay, let's tie it all together. Individual agents balance this necessity to explore and exploit. As a result, they produce complexity. Because if they're not exploring enough, if the system is stable, if no one's exploring enough, there's incredible incentives to explore. If too many people are exploring, then there's an incentive to sort of exploit. What that does is that keeps the dial in between. So we can think of complexity as an emergent property. No one of the agents sets out to create it. It just happens from the bottom up. Now, in the next lecture, we're going to see how complexity is just one of the many possible emergent properties that a complex system can produce. Thank you.